So, good evening, everyone, and a very warm welcome to day two of our FTP. We are really delighted to have you all back and look forward to another enriching session together. The topic for the first session is artificial intelligence for design of composite materials. And let me introduce the honorable resource person for this session. Dr. Shubhabrata Datta. Sir is a research professor in the Department of Mechanical Engineering and coordinator of the Center for Composites and Advanced Materials at SRM Institute of Science and Technology, Tamil Nadu. Sir holds a BE, ME, and PhD in Metallurgical and Materials Engineering from the IIE ST Shibpur. With over 35 years of teaching and research experience, his research interests include materials informatics, composites, and biomaterials. He has published more than 200 research papers and authored or edited 5 books. 15 of his doctoral students have been awarded PhD degrees. A recipient of the Exchange Scientist Award from the Royal Academy of Engineering, UK, Sir has worked at the University of Sheffield, UK, and served as a visiting scientist at Helsinki University of Technology, Finland, Iowa State University, USA, and Abo Academy University, Finland. He is a fellow of the Institution of Engineers India, associate editor of the Journal of the Institution of Engineers India, and serves on the editorial boards of several international journals. Professor Datta is listed in the career-long world's top 2% scientists database published by Stanford University and Elsevier, and received the Eminent Engineering Personality Award from the Institution of Engineers India in 2024. We are really feeling privileged to get such a great academician as resource person. Sir, I think you have already joined.
Yes,
Yes,
I've
sir.
joined.
Okay, sir. So then please unmute yourself, and I think you are already unmuted. Okay, okay,
Yeah.
sir. Yes, sir.
So, so thank you, madam, for the nice introduction, and very good evening to all of you. And thanks to the organizers, the Elite College of Engineering, particularly Dr. Animesh Talapatra. He actually contacted me and asked me to deliver a lecture. So thanks to him also. Let me share first. My slides are visible.
Yes, sir.
Okay. Shall I start?
Yes, sir. Please.
Thank you. So, okay, the topic is artificial intelligence for design of composite materials. It is really inspiring to see that so many participants in this particular FTP. Yesterday also I have joined. I joined and I saw that so many participants were there, hundreds of participants. So it is really heartening to see that so many people are interested in composite materials. Now, in our institute, the SRM Institute of Science and Technology, the Katankulathur campus, it's in the outskirts of Chennai. We have a center for composites and advanced materials. So we work in various areas. Almost 20, 25 faculty members are involved in this particular center. We are doing a lot of different dimensions of work, mostly in the composites domain and some other materials also, like alloys, energy materials, uh, sensor materials. And in case of all these materials, we do both the things, like we do computations and also experimental work. So we have the facilities for both both these things. You can see some research facilities of the center, some research facilities of our center. So we have a decent facility of synthesizing composite materials and also other materials, both metal matrix composite and polymer matrix composites. And also we have a decent simulation infrastructure also for finite element analysis, for different multi-scale modeling technique, and of course AIML. So this is the little bit of background of our center. So let us come to the lecture. My lecture will start with the concept of design of materials, how a material can be designed. In this case, I'll focus on designing the composite materials. Then the concept of materials informatics, how data-driven models, machine learning, these things can be used for designing new materials, materials with improved performance, improved properties. Little bit of concept of design optimization, where we actually use a lot of optimization algorithms for designing the materials. That concept also I'll explain. So after this introductory part, I'll go for some case studies. I'll try to cover three case studies. The first one on metal matrix composites, and then one on polymer matrix composite with particulate reinforcement, and the last one, polymer matrix composite with mm, continuous fibers. But all three applications will be in the field of biomedical implants. So first, to start with design of materials. So any product design, if you know these things, that it start with the empathize, then we start with defining the problem, ideate the problem, create some prototype, then test the prototype. Then whatever shortcoming, we come back to the ideate, the formulation part of it. Again, we try to find the solution, we make the prototype and test. So this is the basic concept of designing anything. Now, in case of a material or any product made from, all products are made of materials. So product depends on product performance depends on the product design. Now, product design depends on two things. One is the product geometry. Any component, any machine, whatever we are making, it's this geometry part. And second part is the materials property. Now, material property, when we are trying to design a material property or trying to achieve a certain material property in any material, so we have two things in our hand which we can control. Those are called composition and processing. Now, composition and processing leads to the microstructure. Microstructure leads to the property, and property leads to a performance. Performance means for a particular application, we may need a combination of several properties. Maybe the strength, maybe the corrosion resistance, maybe something else, maybe a combination of some conflicting properties. All these things comes into picture. So if we think about properties and performance, you can see that this is a very common picture I have used. It is available in internet also. You can see that we want to make when we are trying to make a aircraft wing. So that includes some combinations of properties like its stiffness, strength, toughness, weight, all these things. Now, if one of them is missing, then actually there are some problems. Like you can see, in stiffness is not enough, then it can bend upwards. If the strength is not enough, then it can break. If the toughness is not enough, it can it can go for brittle failures. If it is too heavy, the weight is high, then also we can uh, face problems. So there are several properties, a combination of properties which actually lead to the performance of any material when it is applied to a particular application. Coming to a little bit of evolution of materials, you can see that the application of materials has changed with time. The majority of the materials were initially the polymers. Most of the polymers means the natural polymers like wood, skin, fibers, when it was before Christ situation. Then composites were there, like straw brick papers, ceramic glasses we started using, like pots and these kind of things. Then slowly, when metal came, metal dominated the applications. All engineering applications were dominated by the metals. We started with we started with copper, bronze. Then the Iron Age came. We started using iron. Then different alloys, light alloys, super alloys, titanium. All these things came. And now, again, from the later half of the last century, the things have started changing again on the reverse direction, that we are trying to reduce the application of metals uh, f- due to its different aspects. Like one is definitely the density. We are trying for lighter materials, and then the corrosion properties and all these things. So naturally, polymers are taking a big role in engineering applications. Composites are growing, the applications of composites are also growing. So in this situation, in the in this century, in this particular century, composite is going to play a big role in all engineering applications, due to its certain advantages, mostly due to its lightweight, and also its durability.
కోపం నేను ఫిక్స్ అయిపోయా నేను ఈ మందులు
Designing a material, when we are targeting a particular property of a material for a particular application, there are two approaches we can go for. One is we can go for a lot of experiments, go for trials, experimental trials, and try to find a suitable uh, composition, suitable processing route for which material can be used for the particular application. This is one particular approach, and this approach actually takes a lot of time, and of course expenses are also high. On the other hand, if we can design the material computationally, and then after designing go for the trial, experimental trial, then definitely the cost will be less, time will be less. So naturally, from that point of view, it is the computational design of materials that comes into picture. Now, computation means, we know that computation means modeling, simulation, and optimization. Now, in case of analytical modeling or science-based modeling, you have one governing equation. You start with that governing equation. You try to solve it either through numerical analysis methods like finite element. Yesterday, we had you had a couple of lectures on finite element analysis also, and how it can be applied to composites. So that is one approach. You have some governing equations derived from fundamental science, and that you are trying to solve for a particular component, uh, particular composite, and you are going through some sort of simulations. And that is another approach, that is generally we call the empirical models. Empirical models are basically data driven models, experience models developed from experience, not from the fundamental science. So where we have the applications of machine learning, we have the applications of AI in general. Now coming to composites, these fundamental things we all know. Probably yesterday also we had discussions on this. So we have some composites where particles are there. Particles can be incorporated, reinforced. Then there may be short fibers. And finally, there may be some continuous fiber composites also, which is called lamina. When we stack the different laminas, it is called laminates. And this is one way of mm, classifying the composite materials from the reinforcement point of view, which type of reinforcement you are putting inside. And the other way is to classify the composite materials from its matrix materials. That is, either it is metal or polymers or ceramics. So in case of composites, the properties depends on certain factors, certain variables. We can call it design variables. From the optimization point of view, we call it design variables. Even for simulation, people also call it design variables. So we have these design variables for composite materials, which actually determine the final property of the material. First is the matrix material, which matrix you are using. The reinforcement material, it can be more than one type of reinforcement, which is called a hybrid composite. So whatever, one single type of reinforcement or multiple type of reinforcement, the reinforcement material, the volume fraction of the reinforcement material, how much you are adding, the fiber orientation in case of lamina. If you are going for a continuous fiber reinforcement, then the fiber orientation of the lamina is very much important. You have probably studied, they have discussed about this, that when you are putting the fibers in a lamina, it doesn't act as a isotropic materials, it becomes orthotropic. So number of lamina in a laminate, uh, and so number of stacks, number of layers you are creating in the laminate, and fiber orientations of the laminae. That means the each lamina, each layer, what is the fiber orientation? All and finally the interfacing bond, that is the bonding between the fibers and the matrix, or the say particulate and the matrix. So these are the variables which actually control the final property of the composite material. Now, if we divide these several variables into different length scale, then we can see that in the atomistic scale, so we have some constituents like the matrix materials or the even the fibers, even the particulates. We can model it in the atomistic scale. Then the micro constituents, where we actually deal with the uh, interfaces between the fiber and the matrix, the interface. Then we can deal with the intra-tau matrix, the matrix in between the fibers. Then in the mesoscale, we can think about the uh, designing the tau, that when they are either they are uh, oriented in a single direction, or it may be bidirectional, oven kind of thing. So whatever it is, we can try to think. And finally, we can think about the final laminate or the final component material, where we can use some continuum methods for modeling it. So in different length scale, what I was talking about, we can use in these different tools for these things like quantum mechanics, molecular dynamics, finite element micromechanics, Monte Carlo damage evaluation, laminate analysis. But whatever we are using in all these cases, these are analytical approaches. So we have some governing equations, and most of the cases, those are already derived some scientific from the basic science, from the fundamental science. So we have some known equations we are applying to our system, for our particular system, for our work. In 2011, US government took an initiative. They called it Materials Genome Initiative. And the goal was to decrease the cost and time to market, reduce the cost and time to market by 50%. So the initiative offers a unique opportunity of the United States to discover, develop, and manufacture and deploy uh, advanced materials at least twice as fast as possible and at a fraction of the cost. So naturally, you can understand then when we are trying to reduce the time and cost of discovering new material, generating new materials. So naturally, it has to be a computational approach. So that's why they named it as Materials Genome Initiative, in short, MGI. And nowadays, it is MGI approach is getting used by several countries. It is not only a US factor, but it was initiated in 2011 by the US government itself. So MGI has broadly two components. On the right side, you can see the multi-scale modeling concept, which I have already discussed, that we can model a material, composite materials also in different length scale, and we can use different simulation strategies like density functional theory, molecular dynamics, uh, finite element analysis. In case of metals and metals and alloys, we can use thermodynamic principles, the calculation of phase diagrams. So a lot of things are there which we can use in different length scale. Starting from the, say, the atomistic behavior to uh, the phase transformation, microstructure generation to the final property. All these things, all length scales, we can do this modeling, which is called a multi-scale modeling. And the other approach, which is given in the left side of the screen, that is called materials informatics. So let us talk about materials informatics, because my thing will be all my approaches are based on this materials informatics approach. So in the materials informatics, we need data to start with. Then we have to make some correlation between the data, between the variables. Have to add some theory, that means the existing knowledge. And from that, we generate the final knowledge base. And for the data, we need some data acquisition from either from experimentation or literature. I'll come to this point from where we can get the data. Then correlations can be made through some inference engines, and then physical concepts of the theory that comes in the theory, physical concept of the system that comes in the theory part. And finally, from the knowledge base, we can go for the informatics based material design. Now, in this part, in this whole concept, this inference engine that can be generated successfully or easily by using machine learning. Now, when we talk about data, now it is a common term, that is data analytics. Now, in data analytics, there are different aspects of data analytics that we can, if we go increase the difficulty level, then it can start with descriptive analytics, then go for diagnostic analytics, then predictive analytics, and prescriptive analytics. So we will concentrate on the predictive and prescriptive part of it. These two part we use in our work most of the time. And so data analytics involves the actual analysis of the data, and informatics is the application of that information. So when we are analyzing the data, then it is data analytics. Then what we get from the analysis, if we apply that information for any engineering purpose, that is informatics. So in case of materials informatics, when we design uh, new material using the informatics approach, then it is called materials informatics. So naturally, we can understand that when it is data, it is AI. AI is needed nowadays. Uh, Artificial intelligence, we all know, is a development of a smart system and machines that can carry out tasks that typically require human intelligence. So it is instead of human intelligence, if a machine or a system can work uh, similar to human being, then it is artificial intelligence. Machine learning, which is nothing but a subset of AI, artificial intelligence, where machine learns from data or the machine learns from the information we are supplying to it and develop some correlations so that they can make some kind of new decisions out of it. And deep learning, though I'll not go into the deep learning part, deep learning is subset of machine learning, of course. Now, why data-driven models are required in materials? In materials, data-driven approach is not new. It is coming from maybe last 70, 80 years. We are using lot of data-driven models. You may know about the famous Hall-Page equation, which was generated from data. And then there were a lot of transformation temperatures, um, carbon equivalent, a lot of things were there which were all generated from data. So this empirical modeling or say data-driven modeling are quite common in case of materials engineering. The purposes are analyzing the data to get better understanding of the system. For example, the role of independent variables, developing a mathematical correlation between the inputs and the output, effective when physics-driven models are absent or not effective. So that this point is important because this machine AI ML or say data-driven approaches, materials informatics, this is not for replacing science. When the physics-driven, the science-driven models are absent or insufficient to solve a problem, then only we can go for this kind of approaches. Otherwise, we should depend on the science. Uh, it can be used for generated correlation of simulation and optimization. So we can use it for many systems, particularly for a complex system, say where the number of variables are very high and there is no clear-cut understanding or mathematically expressible understanding of the science-driven approach to develop a correlation between the variables. In such case, there we don't have any option but to go for data-driven models. So that means uh, just for the sake of using machine learning, just for the sake of using AI, it is not correct to use, at least in case of material system. Now, data means we need lot of data. We need data, sufficient amount of data to go for a data-driven modeling applying materials informatics concept. Now, where can we get this data? The sources of data can be various. First of all, uh, some people do like this. They go for doing some experiments. They generate some data, and they finally go for developing one machine learning model. And that machine learning model is just purposeless. You are using it as a ornament only. And when you are yourself is doing the experiments, then the purpose of using this materials informatics or say data-driven model is not there. So we should use data from some other sources. Like we can find some experimental data already published in different journal papers, and we can collect, we can create a database, or there can be some databases available in internet. There are, you may know that there are a lot of data repositories have been developed, and in many data repositories, materials related data are available. And the point is that if you uh, have a interest in a particular domain, particular material system, then you have to search for those kind of data. You may get, you may not. In that case, if the data repository doesn't help, then you can go for generating a database, developing a database out of published data in literatures. So this is one approach of getting experimental data. Other approach is going for simulated data. So simulated data means you can go for simulations in any of the simulated methods, like finite element data, finite element analysis, and use that finite element simulated data for further informatics-based design. I'll show in my third case study, I'll show that how we can use the finite element simulation data for designing a material. Uh, People are using nowadays the material scientists coming from the say physics chemistry background who use density functional theory. Nowadays they are also going for machine learning approaches, materials informatics approaches, and they are using this DFT simulation data for their uh, machine learning for their original data. Now we are talking about machine learning. So in my case, probably nowadays everybody are aware a little bit of machine learning. So, there are a lot of tools for machine learning, and you can use any of it, or you can use several of it and try to find which one is working better. But in my case, mm, the examples I'll show in this work is all based on artificial neural network. So this is the artificial neural network concept. You know probably that it functions by mimicking the human brain. So there are neurons, artificial neurons, which are connected to each other. So there is a forward kind of there is a feed forward approach where initially the signals go in the forward direction. You send the data input variables, then it makes some predictions based on some randomly generated weights and biases, calculates the error, then the error is back propagated to adjust the weight and biases. So there is a process of iterations, which is called the epoch. So based on that epoch, they finally the neural network gets trained. So the neural network learns from the data, and finally it is capable of predicting. Another concept I would like to say about this thing, that is called the surrogate model. Surrogate model, surrogate model is something uh, which is a model of a model. That means when you are not uh, using the actual data. That means you are not using the actual real experimental data and generating a data-driven model, a machine learning-driven model. But you are using some data which is generated from a model. That means, say, it may be a finite element model, it may be a density functional theory based model, it can be a molecular dynamics, thermodynamic based model, whatever. If you are generating a model based on some data which is generated from the simulations of uh, another model, then we generally call it a surrogate model. In my last case study, I'll show that example of surrogate model also, where I'll use the finite element simulation data for my work. Another thing before I go into the case studies, the last thing probably, that is the concept of design optimization. Now, you know, when we are designing something using some kind of, say, mm, analytical methods or some kind of numerical analysis like finite element analysis, if we are doing something, what we do, we have some target performance. We need that amount of stress has to be, stress should not exceed that level, or say the deformation should not exceed that level. In that way, we change the material property. We may, in case of composites, we may change the change the fiber orientations, or in that way we try to find that in which condition the particular component or any whatever you are designing, that is behaving properly. That means that can be used for that particular application. Now, this is called an adequate application. That means it can work for your particular purpose, but that may not be the best design. So, adequate design is something which we can achieve through simulations, repeated simulations with varying the variables, which we can change in actual real life also. So we can do that, and we can find an adequate design. But to find the optimum design, that the best design, we need to use some optimization. So in case of composite materials also, if we require certain properties, and we are using, say, one finite element analysis to find that whether that property we can achieve for a particular any any applications, then we can do that, but that doesn't guarantee that that is the best design. So for the best design of that composite material, its type of fibers to be used, the number of layers to be used, the fiber orientations in different layers or different laminae, that things we need to go for some kind of optimization. And optimization, we know that we have certain parameters to be optimized. Those are called the design variables to find the best performance of the objective function. So basically, optimization can be divided into two broad groups. One is called the classical optimization, where it can be those classical optimizations were mostly derivative based. So we need to make make it differentiate it. So in most cases, it is partial differentiation, like say gradient descent algorithms, scale conjugate gradient algorithms. These are the common classical algorithms. There were few non-derivative based optimizations were also there. But in most cases, the difference there is that in all classical optimization, we start with a single solution, we change the position of the solution and try to find the optimum. And in such situation, what happens that you can mm, there is a possibility that you can reach to the local minima, not the global minimum. And for that, this classical optimization have some limitations. The new concept that has come after the computer has come, that is the population based algorithms, or say meta heuristic optimization algorithm, where which is a basically a parallel computing system where we are handling a lot of solutions together, so, which are trying to find the optimum solutions independently. So naturally what happens that if some solutions get stuck in local optima, others, there is a probability that others will find the global optima value also. So there are different meta heuristics algorithm. Among the meta heuristic algorithm, this genetic algorithm is the most popular and probably the most tested in engineering application. So I use this also, this genetic algorithm as my optimization algorithm. Genetic algorithm is based on the concept of survival of the fittest, that was given by the Sir Charles Darwin. And there are several steps in that. That is crossover, mutation, selection, all these things are there. By that method, the optimization is generated. I am not going into the detail of the techniques because that you can learn from, you may know, or if you don't know, then you can learn from any other sources. Now, I'll come to this point. This is when we are talking about a material performance, and as I already told, that performance means it's a combination of property depending on the application. So we may need several different properties, and in many cases, those properties may be conflicting in nature. Say, for example, strength and ductility. We know in materials, normally in most of the materials, if we increase the strength, the ductility gets reduced. But in many cases, we need high strength, high ductility. Like say, for automobile components, the car body, we need material with high strength, high ductility. So this kind of situation where we need two different properties and those properties are conflicting in nature, in such situation we go for multi-objective optimization. That means more than one objectives, and those objectives are not converging to a single point, they are conflicting in nature. In such situation, we finally we don't get a single solution, we get a set of solutions, that is called the Pareto front. And that Pareto front is a non-dominated solution set of solutions which are better than the other solutions, but they cannot be compared in between them. So they all are good, they all are optimum, but it is not a single solution. Now let us start the first case study. So it is designing of titanium alloy composites for dental implant. So we know nowadays dental implant is quite common. It is a kind of a uh, screw kind of a thing which is fixed inside the jawbone, and then there is a cap which which is fitted at the top of it, which plays the role of mm, the dental part, the teeth. And uh, for these, there are certain factors which governs the selection of the material. Generally, the biomaterials which are used for any orthopedic as well as dental implants, for any hard tissue implants, stainless steels are used, cobalt-based alloys, mostly cobalt chromium alloys are used, and titanium and several titanium alloys are used. The most common alloy which is used is titanium 6 aluminum 4 vanadium, but that material is not meant for implants inside human body. It is a material developed for aerospace application, but it is used as an implant material because it is easily available. It is easily available, but it has a good amount of aluminum, which is not good for health. So naturally, it is not an ideal material for implants. There are other factors that for any hard tissue implant, we need certain properties. First of all, it should have a good yield strength so that it can bear the load. Say in case of dental implants, when we are chewing, when you are putting some things in hard something, trying to break with our teeth, then naturally uh, it 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 has to bear good amount of load. So the yield strength of that material has to be good. And low elastic modulus. Low elastic modulus is something very much important. If you are aware of this or not, that the stiffness of a cortical bone, the hard bone of our body, there are two types of bone mostly. One is called the cortical bone, and another is called the cancellous bone. Cancellous bone is the softer bone, mostly the porous kind of bone, that is called cancellous bone, which is weak. The main load is taken by the cortical bone, and cortical bone has a stiffness of around 20 gigapascal. And if the implant has more strength, more stiffness, or more higher elastic modulus, the implant material has higher elastic modulus, then when the load is getting transferred, the load is taken mostly by the implant. So the bone gets lower share of the strength of the stress generated. And if the bone is not stressed regularly properly, then what happens, it starts depleting the minerals and becomes weak. So for the long term, this kind of materials with higher elastic modulus is a problem. Now in case of stainless steel or cobalt chromium alloys, the modulus is somewhere around 200 to 20 gigapascal. Titanium is definitely better than that. Titanium, or it's that popular alloy titanium 6 aluminum 4 vanadium. they have a stiffness of around elastic modulus of around 105 to 110 gigapascal, which is closer to um, cortical bone, but it is still uh, not near to it. But this is another aspect. So we need a material which has low elastic modulus. We need a material which has to be biocompatible. And if the material has a bioactive surface which can help in generation or regeneration of the bone, then we can have a better integration of the implant with the human body, which is called osseointegration. So naturally, a bioactive surface is also very much required. And skipping these things, so we have to make a model for where we can go for a optimization, which where we can try to maximize the yield strength. We can try to minimize the elastic modulus, and we can reduce the cost also as much as possible, because yeah, there are a lot of alloying elements, and some of them are really expensive. So expensive alloying elements can lead to expensive alloys, final alloy. And as this issue of these dental implants or orthopedic implants, whatever we are thinking about, in each cases, it is mostly a problem of elderly people. So it is better to reduce the cost also, limit the cost to a certain extent. So there were certain constraints were applied for the optimization process. Uh, these are the first two constraints: the coefficient of fibroblast eye outgrowth and the relative growth rate of L929 cells. These two are made constants were put for the biocompatibility factor, so that the alloy doesn't become a non-biocompatible alloy. And mm, another aluminium equivalent is used. This aluminium equivalent, if in titanium, if it is more than 9, then the titanium alloy becomes toughness is reduced significantly. So these were the variables. We generated a variables of the titanium alloy. So these are the alloying elements, followed by some processing variables like solutionizing temperature, aging time, cooling rate, all these things. And we had two outputs: elastic modulus and yield strength. So we developed two different models, data driven from the data collected from published literature. We did two different neural network model, artificial neural network models were generated, one for the elastic modulus and one for the yield strength. There are some simulation studies, not important, I'm skipping it. Now coming to the point that we were thinking about how to make it bioactive. So generally for bioactive, making the surface bioactive so that it has a better osseo integration with the bone and implant has better integration. So generally the approach is to make a layer of bioactive materials, the hydroxyapatite. Hydroxyapatite is nothing but a variance of calcium phosphate, which is similar to the composition of human bone. Now, in case of making a coating or making a layer of hydroxyapatite, there are issues like the stability of the layer and how much it can be active, all these things. So we thought of a different concept, that why don't we make it a titanium hydroxyapatite composite. So its titanium alloy is the matrix, and hydroxyapatite particulates at the as the um, reinforcement, so that it can be um, it can be bioactive, and titanium will provide the other properties also. But the issue was that incorporating hydroxyapatite may increase the modulus of that material. So what we did, we thought of uh, we thought of making a three-layered implant, where the core will be the alloy itself, and there in the outer layer will be the titanium hydroxyapatite composite, and in between we can have a porous layers to balance the increase in modulus due to addition of hydroxyapatite. So the layer looks like this. So internally at the core, it is the titanium alloy. Then it is a porous titanium alloy layer, the second layer, and the third layer is titanium alloy hydroxyapatite. Now, for the titanium alloy design, we have already generated two neural network models, which is correlating between the composition processing parameters with the strength, yield strength, and modulus. So that was one part we have already done. I have showed you. So and now the total structure has to be modeled. So we use the rule of mixture for that. So one rule of mixture to use the to find the modulus and strength of the outer layer where HAP is applied, hydroxyapatite is applied. One rule of mixture for the porous layer where porosity is applied. So we had these different rule of mixtures, and finally we had this the elastic modulus of the total component. We for the simplicity we took a cylinder like thing. Basically, it's a kind of cylinder like thing itself, which will be threaded later. So it started with a cylinder, and so there are certain variables. First of all, those compositions processing parameters are the variables. Volume fraction of the how much hydroxyapatite we can apply at the outer layer, that is another variable. And the radius of the inner layer and the middle layer, these are the another two variables, which are R1 and R2. We call it the R1 and R2. So in this way, we formulated the objective functions, one for the modulus and another for the yield strength. And we used the multi-objective genetic algorithm for this study. And there are the different optimization conditions for which we uh, uh, did the optimization, multi-objective optimization, and we got this Pareto fronts. So these are Pareto fronts for different conditions, condition one, condition two, that is written in at the bottom of the figure, you can see. So we've got several things, and it is found that this red color, that condition three is giving better results compared to this, because it has the solutions are having higher yield strength compared to the others, and lower modulus compared to the others. So we studied how the design variables are behaving behind those Pareto fronts. We studied those also, and we went for some solutions where particular solutions were uh, collected, and on the basis of that, we made the alloy. We made the alloy through um, mechanical alloying concept. We made the three-layered composite and sintered it uh, successfully. The middle layer, the porous layer, was made using some pacers, which are common for making porous titanium alloys. People use it for making titanium foams also. So those pacers we have used to make the porous layer, and the outer layer we have used hydroxyapatite. So this was the concept. From there, we took three solutions out of it, and we made it successfully. And I'm not going for the experimental part because that is not the purpose of this lecture. So it was done. Now coming to the second case study. So it is designing hybrid ultra-high molecular weight polyethylene composites for total knee arthroplasty. So you know that this is this hip replacement, knee replacement. For all these things, there are certain materials like this plastic liner in case of the knee replacement, this material in the hip replacement, and second one the knee replacement. We need some materials which can act as a cushion between when there is a rotational movement in both knee and hip. There are movements. And in those moments, we need some cushioning materials, and that materials actually work in between two metallic components, so that there is no direct metal to metal contact. And for these materials, we require some properties like mechanical properties has to be good. It should have a good strength, because it will all that liner also will face good amount of load. So mechanical property has to be good. There is a The main problem is there is a wear effect. So uh, wear debris are formed, which can have some problems in the nearby tissues and all these things. The biocompatibility of the material, and if possible, if it can be made a bioactive material also. So we merged what we did, when we are searching the literature, we found that people did some research on improving these properties only. But some people used carbon fibers, short carbon fibers. Some people used graphene, and some people used CNTs, MWCNTs, multiple CNTs. So we found that in some cases they have good results in, say, some aspect. Wear properties have been improved by one of the applications. Strength have been improved by other additions. So like that. So what we thought, that why don't we go for adding everything, all three? So all three, if we add all three together, then we may have a good combination of properties. That means the overall performance can be improved. So for that, what we did, we collected database, one database where people have used carbon fibers, short carbon fibers in UHMWP, ultra high molecular polyethylene. Some in another case, people have used MWCNT in UHMWP. In another database we generated, where we found that people have used graphene. So what we did, we merged the three databases together to made a single database. With that single database, our outputs were, you can see in the list itself, it's Young's modulus, hardness, UTS, coefficient of friction, and specific wear rate. So these were the outputs for the models, and we used neural network models, which were good. We did some sensitivity analysis to find which variables are influencing the output in which way, because it was a complex systems we are handling with so many different types of particulates we are adding to it. So we tried to understand the system, get, generate some information, some understanding of the system. So we did that sensitivity analysis, and then we went for some optimization. So when we did the optimization, we found that for the different molecular weights mm, of the of the matrix materials, that is the UHMWP. In market also, you can get UHMWP of varying molecular weights. So, and if the molecular weights are increased, definitely the strength increases, modulus increases. So we were trying to find for which molecular weight we are getting better Young's modulus or better UTS. And also we are trying to find that for those situations, in such situations, for different molecular weights, how the requirement of CNT and graphene, or CNT, mm, graphene and carbon fibers are varying. So from the optimization point of view, we are trying to find those results out of that. use कर सकते हो अगर salt की जरूरत होगी तो तुम ऐड कर सकते हो and बस You can see this is the Pareto fronts, as I told. The Pareto front, where you can see that this is elastic modulus versus UTS. and with the varying, we were trying to maximize the modulus and the strength both, so that first of all, I told you that it has to bear a good amount of load, so strength has to be high, and modulus also we are trying to increase, because uh, higher modulus means lesser deformation during the loaded condition. So that means, if the materials at the liner deforms less, then there will be less amount of possibility of getting wear and all these things. So we are trying to increase both the things, and these are the both we are trying to maximize, and these are the Pareto fronts for different molecular weights of the matrix material. And from that we found that this is the zone where which is better, and for the less material, and also for less molecular weight of the matrix material, and for the high, like 4.5 or something, that matrix materials, how the solutions are varying. That means how the CNT content is varying, how the graphene content is varying. This is similarly, this is a Pareto front for different molecular weight materials for specific wear rate and coefficient of friction. We were trying to reduce both the things together, and this is a three-dimensional plot, because when we are using three objectives together, like modulus, coefficient of friction, and specific wear rate together, or hardness, coefficient of friction, specific wear rate together, then how it looks. So in such cases, we were, say, in the modulus, coefficient of friction, and specific wear rate, we are trying to minimize the coefficient of friction and specific wear rate, whereas we are trying to maximize the elastic modulus, and these are the parallelograms we got. uh, and again, this in this work also, we have went for making the materials. We actually made the different solutions, first with two material, then with two reinforcement, like carbon fiber, and sorry, started with CNT and graphene, then we added carbon fiber, and even one in which I have not shown here, in another extension of this work, we added, uh, we we took the database of hydroxyapatite also. That was the fourth type of particulates, and we made all the possible combinations and characterized it, and we found in some cases it was giving excellent specific wear rate, and which is it is expected that the strength will increase. We are providing harder particulates like CNT, graphene, or carbon fibers. So it is expected the strength will increase, modulus will increase. That was expected. But the thing which we were happy to achieve, that the specific wear rate, in some cases it was really low. And so this was the case of the second case study. Now let me go for the final case study, the designing the FRP fracture plate for periprosthetic femoral fracture. I'll explain it. What is that? We all know that. Sorry, just a minute. Forward to put the power connection. Yeah. So this thing you may have seen somewhere there. This is the femur bone of human femur bone, and this is the fracture of the femur head. It is also quite common, particularly for the aged people. They fell down due to some reasons, and there is a fracture at the femur head, and then the femur head is replaced by this implant. This is this gray colored implant you can see. This is the common implant type, which is inserted inside the bone. They remove the top certain part of portion of the femur bone, that particularly the broken head, and instead of that, this implant is inserted inside the bone, the femur bone, and now we have a new femur head, a metallic femur head. In most cases it is metallic. So it is a metallic femur bone we get. Now, due to the presence of this femur bone, femur implant, there is a possibility of some kind of disbalance in the load transfer. The load transfer may not be in the proper direction. So normally, the normal body weight, the load is transferred in a this way, straight through the two legs. But if there is an implant in between, then there may be some difference in the load transfer, which can create some imbalance in loading. And due to that, and maybe due to an accident also, there may be some kind of fractures. The secondary fracture, this is called the periprosthetic fracture. So it is a fracture which is created either at the bottom, at the lower part of the fracture of the plate, or in between the plate itself, there can be a fracture. So for that, we need some kind of plates. You can see the plates in these pictures. These kind of plates are placed this is the fracture created. The previous implant is there. The second fracture, the periprosthetic fracture, has been created, and in that periprosthetic fracture, you can see that you have to put a plate which is called a fracture plate. So this is the case of periprosthetic fracture and the bone plate. Now the point is that, sorry, it is written here itself. The point is that in case of periprosthetic fracture, so if there is a fracture, mm, and when we are giving load, say we are walking or doing something, standing, then there is a load, and due to load, the fracture ends are coming close together, and that creates a stress at the fracture site. And that stress is important because without the stress, the bone growth is not complete. And if the bone is as we have already discussed, the bone growth depends very much on the stress generated. So for the proper healing of the fracture, a sufficient amount of stress should be generated at the fracture site. So to generate the stress there, what is needed, the plate should get some significant amount of deformation, so that the fracture ends come close to each other. The point is that it can be achieved easily if we go for material with lower modulus, like say titanium alloys. We were discussing about that. We can achieve that if we try to. Generally, titanium plates are used in these conditions. So titanium plates are good enough for that. If we use some other alloys, not the titanium 6 aluminum 4 vanadium alloy, if we go for some other alloys which has a lower modulus, then it will work better. It will work fine. But the problem is on the other way, that when it is having lower modulus, so it is easily going this way, the in the axial direction, but it may go on the other way also, that is the transverse direction also. There may be some movement, and that transverse direction movement will
movement will disturb the
healing process. So naturally, we need a material which has a lower modulus in this direction, or it can have good deformation, axial movement in this direction, but less movement in the transverse direction or in the shear direction. So shear movement has to be less and axial movement has to be good. Now this cannot be achieved from a metallic materials, because metallic materials are isotropic, so they will be having similar kind of property in all directions. So we have to make something which is not isotropic. And we don't know, because the point is that the loading condition is complex. Generally, the load comes in a degree, certain 10 to 15 degrees with the axis it acts on the implant, then from the implant it's transferred to the bone, then from the bone it transferred to the plate. So it's a complex way the things are getting transferred. So we thought of designing a composite plate where there will be several layers, and those layers will be we can we don't know what will be the fiber orientations of those layers. So what we did, so this was the objective, that the axial movement has to be high but not more than 2 mm, and the shear movement has to be low and definitely lesser than 0.5 millimeters. So that was the target. So what we did the finite element analysis of this situation, that you can see that this is the femur bone where that implant is fitted, and this is the bone plate. And we compared, we did the um, analysis for uh, composites having 18 layers of the material of the laminas, 18 laminas. And also we had that we compared with the titanium 6 aluminum 4V material also. So we did a lot of finite element simulations varying the um, layer orientations, varying the layer materials. We layer materials means the fiber material like carbon fibers. We tried with carbon fiber, we tried with um, glass fiber, we tried with flax fibers. So these three fibers we tried, which are commonly available, and the matrix was the epoxy resin was used as the matrix material. So these were the, sorry, I made a mistake. It was 28 layers. 28 layers were used for in the laminate. There was 28 laminas. So it was a symmetric model. So 14 layers in certain orientation, and the same orientation will be repeated for the other 14 materials. So for all 14 materials, uh, for all 14 layers, for the 28 layered composite laminate, we had this all the properties that fiber orientation of layer 1 varied from -45 to 0. The material property of layer 1 varied from 35 to 121. 35 is for flax, 121 is for carbon fiber, and glass fiber is somewhere in between. So we varied like this. So we had total 28 variables, 14 for the fiber layer orientation and 14 for the fiber layer materials. So we varied it randomly. We did lot of simulations to generate the amount of axial movement. We measured the axial movement and the shear movement. So now if you can recall, the target is to reduce the axial movement and, sorry, maximize the axial movement and reduce the shear movement. These were the two models we generated using artificial neural network, one for the axial movement and one for the shear movement. We did some sensitivity analysis also to check how the material property as well as the layer orientations that influence on the axial movement and shear movement. So the objective functions were formed based on the neural network model. So this was one of the Pareto fronts where we are increasing the axial movement and decreasing the shear movement. And this is the objective function. Now, these are the, when we saw the material property, there are two things we observed, that in each, as per the solutions, the Pareto solutions, how the orientations are varying. Now, whatever is the orientation, it is not difficult to make it, because we are going to make it through uh, compression molding machine. So we can do it. We can do for any kind of orientation. But the point was that we made the material property also as a variable. So when the optimization process was suggesting the material property, we saw that they are completely random. So it varied from that lowest 32, 30, 32 to 121 from different layers. Now in the it is not possible to get from markets any fiber like that which is having some, if we provide that, give me a fiber of this modulus, so it is not possible. So we had to concentrate on some materials which are available. So what we did, these are the layer angles first we got. So it also varied from mine somewhere near to -40 to somewhere near to 80 degrees. So these were the layer angles for the 14 layers. So that will be symmetrically opposite in the other 14 layers. Yeah. So what we did, we depending so these were the material properties. I will show you. This was the predicted materials property. These are the layer orientations, and these are the material properties for all 28 layers. So you can see the layer material properties varied from somewhere. It is starting from 45 or something, 50, say 50 or around 50 to around 110 or something. But it varied randomly, and it is not possible to find those fibers. So what we did, we made some corrections. What we made, that we saw that if we take that some higher values of, where higher values are uh, preferred, we make the optimization to choose the carbon fiber, and where when lower values are preferred, we made the optimization. We control the upper and lower bound in such a way that they are bound to choose the glass as the fiber material. So in that way, we went for the optimization again, and this was the new Pareto front. And you can see that in this Pareto front, you can see that this is the fiber, the higher upper bounds, sorry, the higher values of the elastic modulus. That means those layers, layer 1, 2, 3, 5, like that, these layers where carbon fibers are preferred, and in case of the other layers, glass fibers are preferred by the optimization. So, and this is the fiber orientations for the all 28 layers, which were suggested by the optimization process. So then in that case also, we went for making the mm, hybrid uh, composite bone plates with carbon and glass fibers in varying in different layers and in different orientations. And what happened, that exactly that testing, that in that type of loading condition, that testing we could not do, but we have done the general strength and flexural test, the tensile strength, the compression strength test, all these things we have done. And we have found that at least we have got a material which has lower elastic modulus in which is reflected in its composite compression and tensile testing, but it has a better improved flexural modulus, which implies that in the shear direction it will behave in a better way. But yeah, this work is definitely not complete. We are trying to develop that kind of loading condition so that we can check the actual how much deformation it is getting for a standard loading on human body. So this is an ideal case of using surrogate models. So we have generated data from simulations, not from any experimental data, not collected from anywhere. We generated the simulated data for our particular requirement, and we applied the AI approach or the materials informatics approach on that generated data, simulated data. And from that, we generated the machine learning based model, neural network models, and went for optimization, got the solutions. And then with using that solution, we went for the manufacturing. So finally, to conclude that several computational tools are available for designing composite materials in different length scales. Materials informatics can also be applied to complex composite systems where AI/ML tools can be effectively used. Optimization tools can successfully be used for designing composite materials with improved performance. Machine learning based surrogate models can be used for finding the optimum design. So the best design we could find from the machine learning based surrogate models generated from the simulated data. So informatics based design of composite materials can design composite efficiently, reducing number of experimental trials and thus reducing the time and expenses for development. So that's all from my end. These are two books published, authored by me, which deals with this kind of approaches of how to design a material, not particularly for composite. It's a general book for designing materials. These two books will be give you some idea how to apply these concepts of artificial intelligence and machine learning for designing new materials. So I acknowledge three of my PhD students whose work basically I showed here in my all three case studies. Uh, if we are in our center, we are actually open for collaboration. You can utilize our facilities, whatever you have. If you are interested in working in composite materials, even we take PhD students regularly. So if you are interested to work with us in composites, you are welcome to contact us. That's all. Thank you.
Thank you so much, sir. Am I audible?
Yes, ma'am.
Okay, sir. Thank you so much for sharing your valuable insights and expertise. Sir, probably you have not noticed that already participants have started asking questions and they have appreciated a lot.
Yes.
Continuously, they were giving a lot of claps and other emojis actually.
Okay.
So,
Thank you.
yes,
It's kind of
yes,
them.
yeah. Sir, there is a question that I can find in the chat box from Mr. John. Yes,
Ma'am?
yes, please. Yes, please.
Yeah. Hello, Professor. Sir, it's a wonderful presentation, sir, actually.
Thank
From
you.
you started from the introduction to your advanced research. Thank you so much for a wonderful presentation. So I think you have completed simulation, then optimization and fabrication, right, sir?
Right. That's the approach. Yeah.
Yes, sir. Actually, I want to know about what fabrication methods you have used for your process, sir. Actually,
Pardon?
because yes, sir. Actually, the fabrication methods, because you have discussed about carbon and glass fibers. Actually, if we are not fabricating well, there will be a delamination failure will be there. So how we can overcome these issues, sir? Not only that delamination part, that white formation. If you go with hand
Are
label,
you making it, and are you doing this kind of work?
no, it's actually in my PhD in my PhD
Okay.
time I have executed. So these are the problems I have faced actually.
Right.
And in hand
No,
light
then
method, I
normally,
got it. Yes, sir.
pardon?
In land light
But
method, I got
hand lab.
that white's porosity and the misalignment of that
Mm.
fiber.
Yeah.
So
No,
these are the
hand lab method is not good enough. Hand lab method is actually, if you do it in the hand lab method, then there is chances of air entrapment. So naturally, those will be the failure sites from where the cracks will get generated. That is one point. And another issue is that the uniformity of distribution of the matrix material will not be the same
Okay.
between the different layers,
Yes.
and naturally uh, you can land up with excessive excess of matrix material in some places, and lack of matrix materials in some cases. In such situation, what happens there is, if the matrix material is insufficient, then what happens that there is chances of delamination is more. And if is the matrix material is more also, then also that area becomes weak, because the stress is
Correct.
distributed to more on the matrix materials, the failure can. So it is better to go for, in case of laminated composite, it is better to go for compression molding machine. Okay, if you
Compression
go
molding.
for compression molding, you are providing some, initially you make the hand layup thing. You put the resins and create the layers, create the number of layers, whatever you go for that, and put it inside a compression molding, give certain load, and under that loaded condition, let it cure. In that case, what
Oh,
will happen? The material will be distributed evenly. The excess material, excess resin will come out of it, and there is a less chance of any air getting entrapped inside. So the best method
okay.
is to go for compression molding. We generally,
Oh,
for the any continuous fibers, we go for compression molding. We don't depend on hand layup very much. Vacuum infusion process is now compression molding is you have to get some facility of that equipment somewhere. So we have
oh,
that facility, compression molding, but anyway, you have to get that facility somewhere. Cheaper option is to go for a hand layup, sorry, not hand layup, a vacuum infusion technique,
okay.
where in vacuum infusion, actually what happens, it is, yeah, the air entrapment, making it porosity kind of thing, that is reduced. But here also you can have excess of uh, matrix material, which is unnecessary. Matrix material actually reduces the strength.
Okay. And one more thing is that maintaining orientation between the fibers.
Mm,
So
mm.
and that also another issue. And maintaining thickness is very difficult, sir. Actually, I try to control the thickness, but I'm unable to get it. So nearly 2 to 3 millimeter variation is there. So that in that case also I am
that
facing it.
that 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 can also be, yeah, if you go for hand layup, if you go for that vacuum infusion, that will be whatever you are trying to achieve, you will get more than that. The thickness will be more than that, isn't it? And that's due to excessive unnecessarily getting to imparting excessive resins. So that can also be controlled by, if you go for compression molding, because
Okay.
you are
Okay.
putting a load, you are so excess uh, and that load can be controlled. So you can determine that for which load you are achieving which thickness with sufficient amount of resin, not the excess amount.
Okay. So can we control heat, sir, while compressing actually? So
Mm,
in my I'm unable to control the temperature. It's gradually increasing. Actually, I installed some DAQ model to control the temperature on the dice, even though I'm
what
unable to
what 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 was your resin, the matrix
if
material? Huh?
epoxy, sir.
Epoxy.
Ma- yes, sir.
Epoxy temperature increases little bit in during curing, but that is okay. That will not create a problem.
Okay.
That is not an issue, I think. That it during curing, it temperature rises little bit. In many
Okay.
cases, like say in compression molding, you can intentionally increase the temperature if required.
Okay.
Say for some of them, say if you are using some thermoplastic material.
No.
Right. In case of thermoplastic material, you have to soften it during the after you have created the layups of this material. Right.
No.
In
Yes.
many cases, like say, say in case of this implant material, some people are trying with polyether ether ketone as the matrix
P.
material. PEEK.
Okay, sir. Yes, yes, sir.
Now, if it is PEEK, now you are trying to make some plates, fracture plates using peak. So peak is not that you are pouring it in a liquid condition and then it is getting cured. It is not like that. You are adding the hardener. It is thermoset. Sorry, thermoplastic. So you have to melt it and then it will solidify. So slowly. So in that compression molding also, molding machine itself, you can control the temperature. You can increase the temperature and make it liquid and distribute in properly in all the layers.
Sure, sir. Definitely, I will try it on, sir. Thank you so much, sir, for attending my questions patiently. Sir, I heard out our few of your publications, sir. It is interesting work, sir. So
Thank you.
definitely, I will follow your work, sir. I think effective fabrication of the optimized
Yeah,
things. Thank you so much,
yeah.
sir, to organizers for bringing such a wonderful person.
Datta sir, good evening, sir.
Good evening.
Hello.
Good evening. I can hear you.
Thank you, sir. Thank you, sir. Sir, I am calling from Andhra Pradesh.
Yes.
Sir, currently I am doing a fabrication work with my material of aluminium, sir, as a matrix. And my performance is going to be done as a reinforcement with the ash, sir. So I'd like to have a clarity that how far the positive effect will be there and in what way I have to go for further continuity of my work to get successive, sir.
Fly ash.
Yes, sir. Yes, sir. It's a peel ash, sir. I'm sorry for that. It's a peel ash, sir. As sometimes the
Okay.
performance, whatever I have done, I got a good result on basis. I don't have any negative even, but still, yet I am planning to go with a nano material along with this peel ash, sir. So how far it supports me? Will it be a successive? So with your experience, please, I would like to have a blessing from you, sir.
No. It is
Sir.
the question of. I think in this particular ash, I don't know about this, but fly ash people have used previously also in aluminium. There are
Sir.
certain problems. I don't know whether you have faced it or not. That I have never worked with aluminium and fly ash kind of thing. So I don't know, but what I have seen from others' reports and some of my friends working in that area, that there is some issues of weightability of the ash. That means it is not properly mixed with the material. So there are a lot of agglomerations. The homogeneity of the mixing is not good. How you are doing you are going through a melting process now?
Yes, sir. Steel casting machine, sir.
Steel casting
Steel
machine.
casting machine with the
Yeah,
400
yeah.
RPM, sir. With
That is
400
better.
RPM.
That is yeah. Under
And
organ. Yeah.
I made this peel ash to be worked with a ball milling machine, sir. The result was in a positive. I planned for going with a nano. I thought of making as a nano, but after my 30 hours of working upon ball milling, it became as a sub-micron level, sir. So they are comfortable for me to work along with
Mm.
the aluminium, sir. So result is
Yeah.
in positive on way, no negative.
If the size decreases, then the surface energy will be increasing, and then there will be more possibility of getting agglomerated.
Sir,
So
sir.
that is the main problem. What I know about this thing, if you can solve this by it may be by proper stirring of the process, that is one thing, so
Sir.
that a homogeneous distribution is you can achieve, and that is one aspect. Another aspect that there people do some pre-treatments, some kind of surface modifications of the particulate, so that it can have a better interface between the matrix and the particulate. That you can
Sir.
also try to find from the literatures what people have done to make a better weightability of the um, particulates. Then
Yeah,
the
in fact, yes,
possibility
sir.
of
In fact, with
agglomeration.
you, yes, sir. In fact, with you, I found literature is very rare, sir. So within experience, I thought to have some suggestions from you as a blessing. So else, just I prefer this question to you, sir. I found the references very rare, sir. Not of much they have done, but the
Yeah,
things
not much.
will be an experimental part which I am going with fabrication, sir. So else, I need your
Good.
support that I can have one valuable word from you. I expected and I gave a question to you, sir. That's the thing.
Okay, you can
With
be
your
in touch
experience,
with me. Uh,
sir, sir.
Whatever I can help, I'll do it.
Sure, sure,
Thank you
sure.
so much,
Thank you,
sir.
sir. Thank you, sir.
Yeah, thank you so much, sir, and thank you, participants, for your active cooperation and your participation. I think a lot of
Thank you, ma'am.
questions are already there. I can see the chat box that a lot of new questions have already arrived, but you should understand that we have some time constraints, but we will be sharing everything, sir's PPT and sir's details and the contact numbers and everything will be shared to you so that you can contact sir later directly. So thank you so much, sir, once again. And moving forward, we will be going to the next session, or you can say the last session of this day.
And we truly thank you for you too, ma'am. Gave a lot of support to us as we are calling from so far places. It is a need for us to have a solutions for a person whom you are providing to us. Thank you a lot for your goodness, ma'am. Thank you.